everybody, and welcome back to another installment of our Thermodynamics II lecture series. And today's lecture is going to be specifically on gas power cycles, which are made up of two primary modes, reciprocating and gas turbine cycles. So specifically, this week we'll talk about the Otto cold air standard cycles. So let's summarize this. First of all, we call them internal combustion engines. That would be in contrast to what's not internal, that would be external. So external combustion engines, which is what we've been talking about so far in this class, namely engines that work on the Rankine cycle, so steam engines. What differentiates the two is that the products of combustion, in the case of internal combustion engines, are the working fluid. Recall that in the Rankine cycle, where steam is the working fluid, and that's not the product of combustion. We're using an external means to heat up the steam. So examples of IC engines, internal combustion engines, we're going to call them IC engines, would be reciprocating engines, such as what you got in your car for all automotive applications. So that would mean gasoline and diesel platforms. So those are IC engines. So automotive applications typically use recip engines. In contrast to gas turbine engines, those are the ones that work on the Brayton cycle, which we'll see next. Those are more often used for power generating plants, for power generation, as well as aircraft, turbojet and turbofan engines, so propulsion applications. That's what powers, say, an X-35 fighter airplane or a Airbus 320. Little known fact, rocket engines are also IC engines, but we're not going to talk a whole lot about those in these lectures. Instead, we'll focus on ideal models of the reciprocating engines in this particular lecture. And we'll also talk about the power generating form of the gas turbine engine in a subsequent lecture. The cycles that represent these types of engines and that we're going to cover in our analysis are going to be the following cycles. Specifically, we'll look at a few of them, both for recip and gas turbine engines. So for recip engines, for IC engines that are reciprocating, our main bread and butter cycle is going to be what we call the Otto cold air standard cycle. Many words here, and they're all very important for what the model entails. This is also called a constant volume combustion cycle. That's the Otto cycle. It's also called the spark ignition cycle, or SI cycle, and that is the Otto cold air standard cycle. This is what models most accurately what you have in your gasoline-powered car. So this is a spark ignition engine. That means there's a spark plug that initiates the combustion process. In contrast to the diesel cold air standard cycle, which we will also be talking about in this module. This is not a spark ignition cycle. Instead, it's a compression ignition cycle, and it's also called a constant pressure combustion cycle because we're modeling the combustion to take place at constant pressure, whereas in the case of the Otto cycle, we assumed it was taking place at constant volume. This will make a difference on our PV diagram. These, of course, are idealizations of the real thing, both the spark plug engine and the diesel engine. And if we want to be a little bit more realistic for either one of them, we are going to model something called a dual cycle. And a dual cycle is basically a hybrid of the two, where part of the cycle occurs at constant volume heat addition, and another part of the heat addition takes place at constant pressure. Finally, we will talk about the gas turbine engines, which themselves are modeled on the Brayton cycle. And we'll talk specifically about power generation using gas turbine engines in a separate video. All right, moving on and focusing a little bit our attention now on the Otto cold air standard cycle. Let's investigate what all of those words mean. They are, as I've mentioned before, an ideal representation of the spark ignition engine cycle, the SI engine. Spark ignition. Again, this is the constant volume heat addition cycle. And this Otto cold air cycle has two strokes. A stroke is the movement of the piston within the cylinder from the very end of its stroke to the other end of the stroke. So from bottom center, also called bottom dead center in some of your book and your videos. I call it bottom center, all the way up to top center. So that's one stroke. This entire cycle takes two strokes. This is in contrast. I'm going to put this in the right-hand side here, the difference between the real thing. Your spark ignition engine works on 4 strokes, so 2 crank revolutions, 4 times the piston moves from one end to the other. Nevertheless, it's a good model for that cycle. The Otto cold air standard uses air as a perfect gas as the working fluid, and therefore it obeys the ideal gas law, and CP/CVs are constant. That's what a perfect gas is. Whereas what's inside of your car, the working fluid is really a mixture of air, gasoline, and combustion products whose properties really vary with temperature. So it's not quite a perfect gas at all. CP and CV vary with temperature. Again, despite these shortcomings, we're going to find that it's a very good model. Now, the cold part of the cold air standard cycle means that those values of CP and CVs on our perfect gas models are picked specifically at a cold with respect to the cycle condition. So typically that's going to be ambient conditions, say 25 degrees Celsius. So find the value of CP, CV of air at 25 degrees Celsius and keep it constant. That's the Otto cold air standard cycle. There are other idealizations for this cycle. Let's look at a few of them that are important. As I said, there's only 2 strokes, which contrasts with the gasoline SI engine in your car in that there is no intake or exhaust strokes. Those would be the extra 2 strokes that you have in your car. If we were to model them, and we can do this ideally as well, there really is nothing going on there. There's no work done, and it's reversible in the adiabatic, so they really don't add anything to the cycle when we represent them in an ideal basis. It takes quite a bit more work to do justice to those strokes, so we're not going to bother on this first analysis of this power cycle. Similarly, we're going to neglect the forms of stored energy that don't directly affect the work extraction, and that's the kinetic energy and potential energy of the working fluid. They really don't do a whole lot in the case of these IC engines. As I said on the Otto cycle, we're going to assume that the heat addition takes place at constant volume, specifically when the piston is at top center. We'll see this on a PV and TS diagrams in a moment, specifically on the PV diagram, and that also occurs instantaneously. Same with the heat rejection. Happens at constant volume, piston's at bottom center, and it's instantaneous. Finally, we're going to assume that the compression of the working fluid, the air, and the power stroke, which is the expansion of that same working gas, all happen isentropically. So adiabatic and reversible processes here, which is going to make it isentropic. Okay. All right, so with these idealization of the model clearly defined, let's move on and plot them on a TS and PV diagram, see what that looks like. Let's start with the PV diagram. And we're going to do a little sketch here of our piston and cylinder assembly as well. And we're going to make sure that we highlight our assumptions when we plot that on PV and TS diagram. So let's put a little graph for PV and TS. Here's PV. And let's just have another one for TS, one on top of another. And we'll label some state points here to correspond to these various processes that we've already talked about. But let's do a little sketch of the piston cylinder assembly first. All right, there's the top of the cylinder. Here's the bottom of the cylinder. And let's change color a little bit here to represent the piston when it's at top center, or I'm going to call it TC. Your book and some of the other videos that I'm recommending you watch often referred to the old school way as top dead center, or TDC. Modern nomenclature typically calls it simply top center. I like that better myself. And let's use blue here for the bottom center position of the piston, which of course represents the lowest point that the piston can be in the cylinder, and so therefore the maximum volume above the piston in the cylinder, right? Let's make the cycle start at bottom center, so we're going to call that state 1, and that's when the action starts, let's just say. All right, so that would be where we're going to be on our PV diagram. I'm going to start with the PV diagram and the two limits that we've got for the volume at top center and bottom center here on our sketch. Similarly, the atmospheric pressure is going to be P infinity, and that's going to be another limit on our PV diagram. Okay, so here's point 1 where the process starts. And the first thing that happens is we're compressing the working fluid, as we said above, at with no heat exchange, adiabatic, and in a reversible, no friction manner, so that makes it isentropic. And remember, for an isentropic process, PV to the gamma is constant. So that curve between 1 and 2, PV to the gamma is constant. Very important part of our model. Here on our sketch, 1 corresponds to the piston at bottom center and 2 at top center. Next, between 2 and 3, there's an instantaneous heat addition, hence constant volume heat addition, right? The piston can't move, it's instantaneous. Between 3 and 4, and that raises the pressure and temperature. Between 3 and 4, we have our power stroke. The piston goes back down to bottom center. That also takes place in a diabatic, reversible manner, so therefore isentropic. So it's going to have another curve where PV to the gamma is constant between 3 and 4. Finally, between 4 and 1 is instantaneous heat rejection. And so that means the piston can't move, volume is constant. And because the heat is rejected, the temperature and pressure drops, and we're back to state 1, and that's the closure cycle. Now let's look at the areas underneath the curve here bound by P infinity, as you remember from our exergy analysis. Between 1 and 2 and P infinity is going to be the work in that we have to supply to compress that gas. It ain't going to compress itself on its own. And similarly, the area between P infinity and 3 and 4 is going to be the work out that's extracted from the cycle as the power stroke takes place. So the difference between those two guys, which I'm hatching in purple here, is the net work out that we managed to get out of this cycle. This is the money, if you will, that we get out of this cycle. So the bigger the purple region is, then the more power, the more energy we get out of this one cycle. This is on a per cycle basis, so it's energy, it's not power that we're dealing with here. Let's do the same thing on a TS diagram. Between 1 and 2, entropy is constant, so vertical line. Between 2 and 3, that's heat addition, so temperature and entropy go up. 3 and 4, again, isentropic, vertical. And between 4 and 1, heat rejection. We're moving to the left. It's going to look that way. All right. Okay. Similarly, let's and of course at 1 it's the ambient temperature or dead state or infinite reservoir to infinity. And so now we can look at the heat addition that we did between 2 and 3. That's going to be the area between T infinity and 2 and 3, and that's the total heat in to the cycle. What's below 4 and 1 and above T infinity is Q out, what we exhaust out of this thing. So the difference between those two guys, that orange hatch area here, represents the net heat input into the cycle. That would be again in joules. All right, let's apply the first law of thermodynamics, or conservation of energy, to this cycle here and see what we got. Right, it's a closed system, so it's kind of easy. We don't have to use Reynolds transport theorem. So this is a very basic statement that energy is neither created nor destroyed, it can only change form. So the change in stored energy for an entire cycle is going to be the net heat in minus the net work out. Capital E is the stored energy. So thermal energy plus kinetic energy plus potential energy. However, because we're running in a cycle, that's just going to be 0, right? The very definition of a cycle. Properties come back to the original state. So delta E is 0, and that means that for the entire cycle, the net work out must be equal to the net heat in. Okay. Now, since all the processes are reversible in this idealized Otto or standard cycle, that makes this TS diagram particularly interesting because according to the second law, this is the limiting case where the net heat in is exactly equal to the cycle integral of ds over t. Whereas remember, for from the second law, Q in net should be less than that integral. Because everything's reversible, it's exactly equal. So that means that that area in orange that we hatched on the TS diagram is exactly equal to the heat in, and it must therefore be exactly equal to the purple area on the PV diagram. So this is a nice feature of these ideal cycle. Limited value in practice for a real engine, because of course it's not, everything's not reversible in a real engine, but again, for the sake of analysis, while we're learning these cycles, it's a very powerful and useful thing to notice. Okay, let's talk about the performance parameters now, specifically one that you're familiar with, the thermal efficiency. So what's the thermal efficiency of the ideal Otto cold air standard cycle? As always, the thermal efficiency is expressed by the Greek letter eta, eta sub th for thermal efficiency. And, oops, let's put th there. And again, it's defined as the net work out of the system, W.net, divided by the total Q in. So that's the area in red on the TS diagram, not the area in orange, right? If it were the area in orange, this ratio would be 1. So it makes no sense. So the net work out, as we saw above, is the total work out minus total work in, which is the work from path 3 to 4 minus the work from path 1 to 2. And the total heat in is between 2 and 3 on our TS diagram, the area in red. Okay? So if we apply the first law now to try and come up for an expression for this, this is not for the cycle now, this is just for process 3-4, looking at the numerator. The change in stored energy between 3 and 4 must be equal to the change in internal energy, since one of our assumptions is that we neglected the kinetic energy and potential energy, right? And that, according to our statement of the first law, must be equal to the heat in between 3 and 4 minus the work out between 3 and 4. Of course, between 3 and 4, the process is reversible adiabatic. That means that Q in 3, 4 is 0. All right. So we've got that the change in stored energy is equal to minus the workout, or that the workout is equal to minus the change in thermal energy between 3 and 4, or the thermal energy at 3 minus the thermal energy at 4, which is equal to CVT3 minus T4 since we got a perfect gas. Okay, without going through the process, same is going to be true for the process between 1 and 2. Okay, and similarly, the heat between 2 and 3, same thing, right? Straightforward. So let's substitute back that back into our equation for the thermal efficiency, and we've got a nice simple expression here in terms of CVs and temperatures. These three little terms, and I'm circling them here for you to make it clear. Okay. Well, we've got a perfect gas, so CV doesn't change, so all those CVs are going to cancel, and all we're ending up with is a bunch of temperatures, and we're going to simplify this a little bit by rearranging them a little bit. Okay, so we can factor out a T3 minus T2 out of that. Let's see if I can do that. There we go. So I got T3 minus T2 on the left. And so that's just going to give us 1 minus some ratio of differences in temperature here. And I'm going to factor out that T4 over T3 here for reasons that are going to quickly become apparent here. We're going to work on that. And so I got T4 over T3, and I'm going to multiply that by a complicated looking ratio of temperatures here. And we're going to start to investigate the geometry of this engine here, see if we can simplify that. Turns out that that square bracket term has a really clean simplification associated to it. And so our question is whether or not we can express these ratios of temperatures in terms of some engine parameter. And what do we have? And the answer is going to be yes. And what do we have for engine parameter? We're going to define the main one, compression ratio, which is denoted with the letter r, and that corresponds to the maximum volume in the cylinder divided by the minimum volume in the cylinder. So that's volume at bottom center divided by volume at top center. So that's obviously a geometric feature of the engine, right? Once you build your engine, that guy is fixed. And on PV diagram, it's the two limits that bound or cycle. So expressing that in terms of the volumes on the PV diagram, that's V1, V4 for bottom center, or V2, V3 for the volume at top center. Now we also know that for the expansion stroke and the power stroke, that the processes are isentropic. So let's focus on the expansion strokes first of all. So the piston goes from from top center to bottom center, and that process is isentropic, which means that PV to the gamma is constant. And remember that little v is big V, extensive volume divided by mass, but the mass is constant because the system is closed. So whether we deal with P big V or P little v doesn't matter, since m is constant. So that means that it's same as the constant is same as 3 as it is at 4, so I can equate these P, V, 3 to the gamma terms, and I can rearrange them a little bit like this here. And specifically, I can look at that ratio of V4 over V3. V4 over V3, that's the volume at bottom center divided by the volume at top center. And so that's what I've defined as my compression ratio. That's kind of a nice thing to observe at that point, right? Okay. Now we don't have pressure on that expression for thermal efficiency. What we have is temperature, but we'll use the ideal gas law, that's what I'm doing here, to factor that in instead, and I'm going to substitute that in for P. So I've got at the end of the day that T3 divided by T4, T at the top center, the beginning of the power stroke, divided by T4 at the bottom of the power stroke, is equal to this compression ratio raised to the gamma minus 1. Okay. Again, because of the shape of my PV diagram, I notice that that's equal to V1 over V2 to the gamma minus 1, and so therefore that's T2 over T1. So T3 over T4 is equal to T2 over T1, and all that's equal to the compression ratio to the gamma minus 1. Okay, so let's keep that in mind for a moment, but let's look at that T3, T4, and T2, T1 a little bit more for a moment and rearrange that to make it fit that square bracket term we have on the equation for thermal efficiency up on the left there. T3 over T4 is equal to T2 over T1. So if I rearrange that, that means that T1 over T4 is equal to T2 over T3. And that's what I've got on the numerator and the denominator of my square bracket. So lo and behold, they're the same. And so therefore, they cancel out. I get 1. And so that entire thing is equal to 1 minus T4 over T3. And again, T4 over T3 is the compression ratio to the gamma minus 1. So the thermal efficiency of the ideal Otto cold air standard cycle is only a function of the compression ratio and the ratio of specific heats. A very, very simple result, right? So it's just how I model the gas. That's going to specify my gamma and the geometry of my engine. That's the best possible thermal efficiency that I can possibly have for my engine. It suggests that the higher I make that compression ratio, the more efficient my engine is going to be, doesn't it? All right, let's look at another important, we'll talk more about that, of course, as we go along. But first I want to introduce another very important performance parameter, the MEP, or the mean effective pressure. MEP is defined as a constant pressure, a constant number, that if we were to apply it to the piston during one stroke, so from top to bottom, the expansion stroke, or power stroke, the work that it would produce would be the same, as the net work net work that's produced by the full cycle of the actual engine. Okay, so MEP is that constant pressure that does the same amount of work in one stroke as the full cycle does by subtracting the work produced minus the work going into the compression of the gas. So let's see if we can express that value. It's kind of nice, right? Because on a PV diagram, it would be just a horizontal line, a straight line from top center to bottom center. That would be my MEP. And that would correspond to the area in purple that we had before. Let's look at the little sketch of our cylinder piston layout here, and let's look at what that MEP actually does and see if we can express it in terms of different parameters. So let's see. The displaced volume, V sub D, we often call it V sub D, is the volume that's swept by the piston as it goes from top center to bottom center, and the area over which the gases are acting is A sub P. That's the piston area. So the displaced volume during expansion, the power stroke, is, as I said, V sub D, displaced volume. And that is going to be equal to the area of the piston, the cross-sectional area of the cylinder, the area of the piston, times the length of my stroke, L. A sub P times L is V sub D. All right, so let's try and weave that into what we got in terms of work and MEP here. So the work done in one stroke, which is what the MEP is going to do, is equal to force times distance. Force, of course, is pressure times area, and I've just defined the terms I need over here. And the distance is going to be the stroke length, L. So pressure MEP times A sub P times L is what I got. If I rearrange this a little bit, it's clear that that's equal to MEP times the displaced volume, and that's the work done during one stroke. So, in other words, if I rearrange this in terms of MEP, MEP is the work done in one stroke divided by the displaced volume, V sub D. Okay, and the work done in one stroke, by definition of MEP, is going to be the net work done in the cycle divided by V sub D. Okay, so that's on a per cycle basis. More conveniently, or more commonly, we're going to talk about that on a per rate basis, and this is a cool engines application of L'Hopital's rule. Do you remember L'Hopital's rule from your Calc 1 class, most likely, or maybe even AP calculus in high school? Basically, what it says is that a ratio of two functions is equal to the derivative of the numerator and the denominator. So I'm going to take the derivative on the numerator and the denominator with respect to time, and so I'm going to get on the numerator, the derivative of work with respect to time is the power produced, and the denominator, the derivative of volume with respect to time, is the rate of displaced volume. So let's let n be the number of revolutions that we have per unit time. So that's the RPM of the engine. Okay. Next, the rate of swept volume, which is the denominator there that we have on our expression here from L'Hopital's rule, is going to be the number of power stroke times time divided by time times the displaced volume, okay, which is equal to revolutions per unit time times number of power strokes per revolution times V sub D. Now, revolutions per unit time is N, the RPM. Number of power strokes per revolution is 1, since every revolution we have 1 power stroke, times V sub D. Notice that if we had a 4-stroke engine, that would be 1/2, right? We would have 1/2 a power stroke. So the expression that we're going to get for MEP is going to be slightly different for gasoline 4-stroke engine than we do here for this ideal cycle or 2-stroke cycle. Let's call P the power produced by the engine here to make your life a little bit simpler. And let's substitute all this into our expression here for MEP. So numerator is just going to be P, the power produced by the engine, and the denominator is going to be N times 1 times V sub D. That's the rate of displaced volume. So that's our expression for the Otto cold air standard cycle. And if we had our 4-stroke cycle, then we would have 1/2 there on the denominator instead of 1. That would give us 2P over N sub V sub D for for a 4-stroke gasoline engine cycle. This is a performance parameter that's very important in basically normalizing the design of the engine in terms of displaced volume. You can make a lot of power with a very, very big engine, but that doesn't mean that your design is good. All right, that's it. We're done for this week. We'll continue on next week with the Brayton cycle. Enjoy the rest of your day. Take care.